So generally, cryptography protects communications and data. And digital signatures sign messages and verify messages, and hashing functions create unique fingerprints of data. And all these three components are needed for blockchains to function. Cryptography dates back decades, was first used for encryption during World War II for military communications. Modern crypto combines math and computer science to protect systems from attackers. Cryptocurrencies are named for the essential role that cryptography holds in making blockchain secure and possible. Now, what they do not do is create absolute privacy. I mentioned that on Tuesday, in that on blockchain, all the data is actually public, and you can follow the money. It is pseudo-anonymous in that you're not able to necessarily associate with an address with a particular identity, but you're still able to follow all the transactions that an address has made. Digital signatures use public-private key pairs. Public key is used for identification, like a username or an address. And then a private key is used for security, like a password. And a private key is used to sign messages to create digital signatures, which can be verified as belonging to the public key. And we walk through some examples. And then hashing functions accept any type of data to generate a unique ID called a hash. The same input will always produce the same output, and it is practically impossible to forge unless you are dealing with a hashing algorithm that is old, or maybe quantum will break some hashing algorithms. And with hash functions, you can easily compare data to see if it's the same. The other property that is not mentioned on this slide, you're not able to go back from a hash to the original value. It's kind of like a one-way thing. So now we'll kind of go through each of these areas in more detail. So if we're thinking about cryptography, there is symmetric cryptography. And this is essentially where a single secret key is used to encrypt and decrypt traffic between participants. And it is used all over the place. It is used in modern internet communications like HTTPS or SSL to protect users from eavesdroppers. And the reason why symmetric cryptography is used is that it is very fast, as opposed to asymmetric cryptography. But it has the issue on how to exchange the key. Because let's assume I access a web server. If we have the same key, great. Then we can encrypt and decrypt the traffic between us. But how do we get a shared key in a secure fashion? And so basically here you have Alice and Bob that want to exchange a message. They both have the secret key. So Bob encrypts the message with the secret key, and then Alice is able to decrypt the message with the same key. So that's symmetric cryptography. Is this new? Is it already well known? Did you cover this maybe in other courses? Yes.
Yeah.
Yes. Okay. All right. Well, I can move a little bit faster. Asymmetric cryptography is basically where you use a public and a private key. And the neat property of this mechanism is that you do not need to exchange keys. Or a secret key. Let's put it that way. You still need to exchange keys, but not the secret ones. And basically, you have a public key that is used for identification and is known by others. So you can generate, your public-private key pair. You keep the private key, and the public key you can put on the internet. And it needs to be somewhere on the internet, or it needs to be accessible, because if you want to send a message to that user, you need their public key. So there's really no secret being exchanged, but it is much slower. And so the example here is, again, Bob and Alice, they want to exchange a message. So Bob, sending a message to Alice, will encrypt that message with Alice's public key. Note the public key is not secret, it should be exchanged. So Bob has access to Alice's public key. And so it uses that to encrypt that message. And then optionally, Bob can use the private key to sign that message, basically indicating to Alice that, hey, this message is really coming from me, from Bob. Then he sends that encrypted message to Alice, and then Alice can use Bob's public key to verify the signature and use Alice's private key to decrypt the message. And so now basically a message has been sent, nobody was able to eavesdrop, and Bob and Alice were guaranteed that the origin was Bob and the recipient was only Alice. So that's asymmetric cryptography. And so if we're thinking about in context of a blockchain, you have essentially a transaction. Bob wants to send 10 ETH to Alice. And basically the from and to is the public key of Bob and Alice. And then Bob signs that transaction with his private key. And so now think of Eve as an attacker. They see that transaction. They switch out the to address from Alice to Eve, but they're not able to generate the signature because they don't have Bob's private key. And therefore, that transaction is protected. Going back to the web context, so SSL. So if you're contacting a web server that uses HTTPS encryption, that traffic is encrypted using a symmetric key. But before you have that key, there is a, kind of like a handshake or a set of actions that are taken place that allow you to exchange a private key securely. Or not a private key, a key securely. So first, what happens is the user contacts the web server and requests the web server's certificate. So that's when you go into the web browser and you see the little locked icon, and you click on that, you actually see the certificate of the web server. So that's public. It's essentially the public key of the web server. So the web server sends back the certificate to the user. And now there is something that happens that is centralized. Essentially, you contact the certificate authority to verify that the web server certificate that you just received from the web server is a valid one. That's why when you have a web server and you set up SSL, you first need to obtain a certificate, and you get that from a certificate authority. Then the browser basically now has a public key of the web server and knows that that public key belongs to the web server through the certificate authority. And then basically what the web browser can do is encrypt the browser's public key with the certificate. So now basically both sides have the public key. And it's signed as well when it gets sent back. And so basically now you have the public key on both sides. You have the private key on both sides, and now you can essentially exchange a secret, right? And I don't know who does it, the web browser. So the web browser generates a secret, encrypts that with the web server's public key, signs it with its private key, sends that over to the server, and then the server is able to say, verify that it's coming from the browser and is able to decrypt it. And now they have a shared secret key that they can use then going forward using symmetric key encryption, which is much faster. So, very similar example to what I showed earlier with Bob and Alice, but it kind of includes how to exchange the public key. Now, an Ethereum wallet, or a crypto wallet in general, first of all, the term wallet is a misnomer. A wallet kind of implies that you have, credit cards and dollar bills stored in it. But that is really not the case for blockchains. What blockchain wallets or crypto wallets actually have is merely the private key. And that allows you to sign transactions and submit them to the blockchain. The digital assets are actually stored on-chain, right? If you think about the example where there was a transaction, sends Alice 1 ETH. Alice is the public key. After this transaction, Alice has 1 ETH, and that is stored, let's say, in a ledger. So think of like, what Alice has 1 ETH. And now for Alice to operate on that 1 ETH, Alice needs to sign a transaction where it's from Alice to Duke, amount 1 ETH, and it needs to be signed by Alice with the public with the private key. And that private key that is stored in your wallet. Now, when you install a wallet, a private key gets generated randomly using a random number generator on your device that usually takes into account also human input like mouse movement to get really true randomness. And the key is generated out of, it has a key length of 256 bits. And that means it's, exceeds the number of atoms in the universe. So no one can really guess the private key. Now, can you think of a weakness during the generation of the random key? Yeah. Anything else? If you don't have true randomness, then maybe it generates keys that can be guessable. And there was an attack last week where somebody used a tool to generate a private key that had a vulnerability that essentially wasn't quite random. And that allowed you to guess a key. And somebody stole $160 million last week because of that.
That person used some kind of library.
Used a tool. It was a tool to generate vanity addresses, and vanity addresses are, so think of like an address usually looks like 3A, B, 4, 5, 6, right? Like it's random. That's how an address looks like. And this tool allows you to generate vanity addresses that started with, let's say, 5 zeros. So they use the tool. I'm sorry? No, it has nothing to do with age. It's basically they just wanted their address to look cool. You could also, there's other addresses that starts with dead, right? So you wanted to have a particular string in the address, and so there was a tool that allowed you to generate that, and that tool had a wasn't quite random, but it wasn't like 256 bits, and so that allowed you to then generate the private key from the public address, and you were able to steal $160 million last week. Yes, sir.
Generated the private key using an algorithm that is definitively not going to be random.
That's right.
And he knew that. So
Well, they didn't know that.
sounds like a classic insurance scam. They stole my money. Did he insure his Ethereum or something?
They did not know that the vulnerability existed. Everybody thought that tool was secure, and it was used by thousands of people. Well, there is actually decentralized insurance companies. Yeah. So when you generate a wallet, essentially you generate a private key. Hopefully it's random. So don't use, I think it was, what was it called? Profanity was it called? Was the tool called that generated these addresses. So don't generate it with profanity because there's a vulnerability. And then it gets stored locally on your machine or on your device, on your phone, your machine. What risk does that bear? Or keystrokes? Yep. So if somebody has access to your computer, they can steal the private key. And then what can they do with the private key? Steal all your digital assets. And so that's why you should probably not have your wallet on a regular device where you download a whole bunch of applications, because if it happens that you're downloading malware that then steals your private keys, all your digital assets are gone. So I would recommend a separate dedicated device, or something called a hardware wallet, which is a special USB key where the private key is stored on specialized hardware, a secure enclave that cannot be accessed directly. The device can be used to sign transactions, but you cannot get the key from it. So that is much more secure than having like a software wallet on a hot wallet on your device. Also, phones, probably more secure than your Windows machine or your Mac machine. Because the phone is much more locked down unless you jailbreak it. I mean, you know, on my Mac, I can install anything, right? On your phone, you have to go to the App Store, right? And so there's also a better separation in terms of processes. Not 100% secure, but again, I would recommend a hardware wallet as opposed to either of those options. The public key is generated from the private key, and a generator point G on the elliptic curve is picked. And so what that allows you to do is also to generate multiple public addresses from the same private key. And we'll see how that looks like. So you have a private key, it picks a point G on the elliptic curve and then hashes that. It's a Keshak 256 hash, and then it uses kind of the last 20 bytes as shown here as your address. Keys are generated offline. So the interesting thing is when you generate a wallet and you have your Ethereum address, blockchain has no knowledge of that. So you could theoretically generate a public-private key on a device that's never connected to the internet, and then ask people to send you digital assets. All right, let's look at how that looks like. So let's see here, Metamask. So the assignment for next week is to do exactly what I'm doing now, hopefully. Metamask. So I installed Metamask. Oops. So Metamask is a browser plugin, not the most secure wallet, because browser plugins also have access to all your website history, but just for demonstration purposes. So you install it. So now it will ask you, hey, do you have a secret key that you already want to import, or you want to create a new secret key? So we'll create a new secret key, and then it's going to ask me for the password. And that password is really used to essentially encrypt the private key locally on disk. Not terribly secure, but it at least is a layer. So it's just kind of to protect your yeah, we'll skip that. Okay. So now what happened is it generated a private key, and it will give you a mnemonic that is easy to write down, because a private key, if you look at this slide here, that's the private key. It's a long hex string. That's going to be super hard to write down. So it gives you these 12 words that essentially are a representation of the private key. And just kind of copy paste, because it will then next ask me, hey, did you write it down? So pattern, fire, menu, diary, script, change. So basically, there's a list of, I don't know, 50,000 words that it picks from, and then the order is important. So that is essentially a private key. So if you write that down, and let's assume your machine goes up in flames, and you install MetaMask on a different device, you essentially enter that key, and basically your digital assets are secure, because your digital assets are not stored on the machine. They're stored on chain. The only thing that is stored is the private key. All right. So now we have a wallet. That wallet now has this address. That's my public key. So if you now want basically somebody to send you Ethereum, you basically give them this public key, and they can start sending it to you. You would never give them the private key, because that's basically you give them the digital assets. Send them the public key. So this is account 1. Now you can create additional accounts. Name them whatever you like. And these accounts all now have different public addresses. And there may be some, hygiene that you may want to have, similar to how you have in your bank account, right? You have a checking account and you have a savings account. Similarly on chain it's much easier to have multiple accounts, right? You could have, a hot wallet, you could have a kind of savings wallet, you could have a trader wallet, you could have an NFT wallet, right? To kind of separate wallets and kind of reduce your risk. Also, if you want to be more anonymous, you can create additional wallets, like throwaway wallets, right? Where you basically say, hey, I'm going to do this trade and then never going to touch that wallet again. They all have the same private key, that is right. However, you cannot link them together based on the public key. So now you have 3 accounts, there's 3 public keys. Nobody on chain could say these all belong to the same private key. But if somebody steals your private key, they have access to all 3 accounts. One more thing that I want to point out here is Metamask works on multiple blockchains. And we will be working on Polygon, which is a sidechain to Ethereum that is cheaper. You have to add it. And if you look at the assignment instructions, it shows you how to do that. Because you're for EVM compatible chains. So that means kind of the same opcodes, the same instructions, kind of the same storage, smart contracts, etc. Metamask is able to interact with multiple blockchains. And so one thing to keep in mind, so you may have digital assets on Ethereum, and you have digital assets on, let's say, Polygon, which are 2 different blockchains. You can manage them all with the same private key, but the digital assets reside in different blockchains. Okay. So install a wallet. And so now let's go back to, so I created just a dummy wallet, right? It does not have any digital assets in it. And here I have a wallet that actually does have digital assets. So this is on Polygon. And it has now, 18 Matic in it. And we can look at the, oops. It's an excellent question. There is layer 2s are categorized into sidechains and either rollups or ZK rollups. Optimistic rollups are ZK rollup chains. And sidechains do not inherit the security properties of the underlying chain. It's basically a separate blockchain that kind of integrates well with the main chain. Optimistic rollup chains like Arbitrum and Optimism, and then zk-sync as the zero knowledge rollup chain, they inherit the security properties of Ethereum. So they are as secure as Ethereum. Okay, so what we're looking at now is a block explorer. Block explorer is essentially a web UI on top of indexed blockchain data that allows you to kind of graphically explore the data. And so what you're able to see here is essentially all the transactions associated with my account. And you see that, initially it was funded with 20 Matic, and then I sent some Matic to another account, etc. And then I did an approve. I don't remember that. Anyway, okay. So let's use the wallet to send some ETH. So here I have my account, 18.79 Matic, sorry. And now I'm going to go send Matic to my second account. And now basically here, what it is asking me is to sign that transaction. So basically locally what it did, it generated the transaction, just like what I said over there. I'm sending from account 1 to account 2, 0.1 Matic, and I am signing it with the private key of account 1. And that then gets essentially packaged up and sent to a node on chain. It will sit in the mempool for some time until a miner gets the right to do the next block. It will then pick it out of the mempool and mine it. So let's do that. Back up my key. So it's going to say here it's queued. It already given me a, no, it did not give me a transaction ID yet, but oh, there it is. Today is the 29th. Okay, so that was very quick, and that was very quick because we're on Polygon, which is a sidechain that sacrificed security for transaction speed. Now let's look at it in the block explorer. So you see 35 seconds ago from account 1 to account 2. And then there's some transaction fees. So I paid, I mean, literally nothing. 0.0011 cents. I mean, there was something being paid. And now if we look at my wallet again, it has 0.1 Matic less, and my other account has 0.1 Matic more. So that's basically, oh, let me show you one more thing. So you have a private key in your wallet, and that allows you to sign transactions that are then sent to chain and then mined. That's one way you can use that private key. It can also be used to log into websites. Usually the way you log into websites is you sign up for an account, you create a username and password, right? And then you later on come back and provide that username and password. But you already have a secret locally stored on your machine, which is your private key of your wallet. And so what that allows you to do is authenticate with websites. And so Forta application allows you to sign in with your wallet. And so you basically say, here's my wallet, and I'm going to connect it. And then I'm going to sign this message. And this message is really just a message that gets signed and then sent to the website. It's not going to be sent to the blockchain. And that basically allows the website to determine, hey, that browser that just connected to me has that private key. And I can identify that user based on the public key that is associated with that private key. And so it's an authentication mechanism that does not rely on usernames and passwords, which I think is pretty neat that, wallets allow you to do that as well. Any questions?
Like accounts based in Russian where I can export my private key.
Yeah, there's an option to export your private key, and let me get that back to my other browser. No, you only have one private key, because basically think of the elliptic curve. You have an elliptic curve that is basically associated with your private key. You have a point on the elliptic curve that gives you account 1. And then it moves onto the elliptic curve. That is account 2, etc. And so when you export your private key and then import it, it will generate that account. And then when you click plus and say second account, it will hop to the same spot and generate that account. So you only have one private key, multiple public keys. Did that answer your question? And so in terms of where to export that private key, settings. Oh, hang on, I'll have to look. Oh, it's somewhere.
You can click on the yeah. Oh, no, not that one. The column one. Can you click on? Can you click the X button? Yes, that's, yeah.
Account details. Export private key. Yeah. So then let's look at this. The account that I just generated, and there's your private key. And so that looks like this. But if you go to, I just saw in settings, it also gives you an option to reveal your secret recovery phase. No, that's the secret recovery phase. There you go.
That is the secret phase is the one that not changed, right?
It's essentially the same thing. It's just a different representation. And but the secret phase is not something that you can easily utilize, let's say, in Web3 API. For that, you actually need the private key. And so for programmatic access to the chain, and you'll have to do this later in the course, where you create your account, you have to export your private key and put that into your code to then programmatically interact with the blockchain without Metamask. Good question. I don't know.
So if we lose the secret key, we lose the assets, right?
Yes.
Okay, so that might be then to like put a level of abstraction and make it words.
Yeah, absolutely. For backups, this is the way to go. And you can even be more secure, right? You could basically now write this down on 3 pieces of paper and distribute it. Yeah, I mean, there's always, there's this guy who was digging through trash for his hard drive that apparently had some Bitcoin on it. Yeah. All right. So it makes sense in terms of what a wallet is and where the private key fits in. All right. I'll spend a few minutes on this. It's going to be fairly quick. So breaking symmetric encryption. So, there's various algorithms out here, and these are really just toy examples that kind of illustrate some of the ways you can break encryption. I mean, it's a whole field. So this is just, a toy example. So a Caesar cipher just basically just shifts letters, right? So we shift it by 5, so you can take my name is Christian, and it will encrypt into the string on the right, and then to decrypt it, you just shift it the other way around. Let me make this bigger again. So now let's assume you have a text like this. How do you decrypt it? Now, obviously there is brute force you could use, right? You could just try all the different shifts and see whether it works, and whether it reveals something in the clear. But there's also techniques that you can utilize where you're exploiting essentially the fact that the underlying data has a certain distribution. So if it's an English text, well, you know that the letter E is much more common than the letter Z. And so you're able to essentially do the frequency analysis on the text here, right? And say, well, which letter is most frequent? And that's kind of what is shown on the bottom here. And you see most frequent is the letter V. And so now that kind of implies you have a shift of 17 based on just those two data points. And if you do that, then it basically allows you to decrypt it. So they're all slow. And if you look at the book, there's probably a gazillion exercises if you're into this sort of code breaking. Break this one. I'm sorry? No, I think it's just cipher. CISA cipher. Yes. Yeah.
We have two easy bills. After that, you can try the next comment. You can see it's just
To be completely honest, I don't remember what it decrypts to, but I'm just waiting for you to solve it.
something P. It's like Ethereum is P. Oh. Yeah. Yeah, 6-1. Yeah. Yeah. I was guys like it's definitely Ethereum and it matches E and like finish really long. Is something you have to is is O or something. Ethereum is O anyway. This one something one of the here the most used currency or something like that, I guess. I don't know. Yeah. I think you can this one
There you go.
Oh, okay.
So Ethereum is one of the most used blockchains. Is one of the yeah. But I mean, I think basically what I heard was, oh, you look at kind of short words, right? You could do frequency analysis, you could do some brute forcing, as well as looking at capitalization, right? Like, so, but obviously the toy example, very easy to break. Now this is the Enigma machine that was used in World War II by the Germans to encrypt essentially messages, and that was broken by the British. Oh no, the Polish. Yeah, exactly. Now the really cool thing about this machine, and I actually I went to a museum, actually was able to type on it. It kind of, as a cipher encryption, it kind of shifted the entire text, a fixed amount of characters. And what this machine does, it kind of varies the number of shifts that are happening based on a code that is pre-configured. So things like frequency analysis become really no longer possible because an E could move to a V or a T, right? It kind of looks much more random. So I don't know exactly how they broke it, but it was a cool innovation at the time.
It's not like the most thing, but probably Hitler.
Yeah, I will. Yeah, probably. There are probably many of them in there. All right, we'll no longer have a break. We will go home. But next time we'll catch up on the remaining encryption content. So we'll talk about hashing and then Merkle trees, and then briefly look through the advanced topics. That's what I hope that we'll get through on Tuesday. If we look at the syllabus, I would ask you all to install a wallet. Doesn't have to be Metamask, any wallet will do. But I want you to be able to, have access to private key and then sign transactions with it. Cryptocurrency. For all the homework assignments, we will be working on a test net where you can get the currency for free. If you will be developing Forta detection bots, then you will need a little bit of Matic, but it's going to be like 50 cents worth of Matic, like very cheap. But if you want to play around with some of the decentralized applications, like do a token exchange, provide liquidity, register name service, whatever, then you do need real currency because those applications are not implemented on testnets in a reliable fashion. So I would recommend it. Well, so the assignments, these are not graded. So the first 3 are not graded. I just kind of rely that you do it. And if you have questions, let me know it. I mean, the first one is install MetaMask. The second one is install your development environment. The third one is install your development environment again, like more to it. It's kind of a prerequisite for the following assignments. So for development, you can use whatever. Yeah, for Solidity development, you can use for whatever. There's a Solidity compiler. You can use TextEdit or Notepad, theoretically. You'll have a difficult time with that. There are specialized development environments. Remix is one of them that we'll demo. And that also has debugging functionality, which is super useful, especially with some of the red teaming challenges. So you most definitely should use Remix. And then I personally also use Brownie with Visual Studio Code.
All right.
So Hard Hat is more JavaScript, Brownie is more Python. So it depends on where you're drawn to. I'm more Python. I use Brownie in Visual Studio Code, but JavaScript, it's Hard Hat and Truffle. It is Hard Hat, but then you're stuck with JavaScript. Well, so just to clarify that, the development of the smart contract is in Solidity, but the scripts, like for testing and deployment, those are then in JavaScript or Python. A host, it's kind of like for management of kind of the development process. Let's put it that way. Like, yeah. Any other questions? All right. Thank you all.